Under ideal conditions, a certain bacteria population is known to double every 3 hours. Suppose that there are initially 100 bacteria. What is the size of the population after 15 hours? Well, 15 hours represents 5 doubling periods, meaning that its one doubling period is 3 hours, because 3 times 5 is going to give us 15. So if we take 100 and multiply it by 2 to the 5th, well, that's going to give us 3,200. So the size of the population after 15 hours is going to be 3,200. Now, what is the size of the population after T hours? Well, again, when it says initially, right, that means that 100 represents the initial amount. So in our first part, we know that that would be y, which is equal to the initial amount, times the value of 2, because it's doubling, raised to the power of 5. And so if we want to know what is the size of the population after T hours, well, what do we know? We know that in T hours, there will be T divided by 3 doubling periods. The initial population is 100, so the population y at time t is going to be the following. So it's going to be y, which is equal to 100, which is the initial population, times 2, and now our exponent for the base of 2 is going to be that doubling period, which is t divided by 3. So now in part C it says estimate the size of the population after 20 hours. So what that means is that we're given the fact that t is equal to 20, and then we're going to plug it into our equation from part B. So y is going to equal 100 times 2 to the 20 divided by 3. And then let's go ahead and put that in our calculator. So we have 100 times 2 to the power, we'll put this in parentheses, 20 divided by 3. And that equals approximately 10,159. So the population is about 10,159 after 20 hours. So now let's take a look at part D. Part D says, graph the population function and estimate the time for the population to reach 50,000. So that means we're going to have two equations that we need to graph. The first equation is our function, which is y, which is equal to 100 times 2 to the power of t divided by 3. And then we can call that y1. And then our other function, y2, is going to equal 50,000. Let me write that again. Okay, so we want to figure out, okay, where does it intersect? Now, we're going to go ahead and put this in our graph. Okay, so our first is 100 times 2 to the power of, we're going to call it x so we can verify it on our graph here, divided by 3. Okay, and then our second graph is going to be y equals 50,000. So let's put in our dimensions. So we're going to go from, let's say x can go from 0, we'll just put in, let's say 40. Now since it's going up to 50,000, let's go from 0 to 60,000. Okay, because now we can see where the point of intersection is. Okay, so now that we can see the point of intersection, and we can see that at x is 26.897, we can say that the two curves intersect at 26.9 approximately. So the population reaches 50,000 in about 26.9 hours.